Hello everybody, welcome to Chember's tutorial. This is our fourth lecture on the general organic chemistry, and in this lecture we will be discussing about some extremely important electronic effects. These are your inductive effect, electromeric effect, resonance and hyperconjugation. As you know that whenever we are going to discuss the stability of some compound or whenever we are going to discuss the acidity or basicity, acidic strength, basic strength of some organic molecules, then these electronic effects plays a very important role. So we need to discuss them, and in this class you will know only the theory part, that means the basic theory. I know that it is a very basic thing which you have already studied from your class 12 level, but here I am going to recapitulate your basic, and the thing is that you should have a clear-cut knowledge about the basic things, because after that we will apply this thing to our MCQ solving session. And you know that from our lecture number 5, that means I will upload the videos on the ChemCQ GOC playlist, and there you will find only MCQ solving. Okay, the MCQ solving session will start very soon, and in that case you will learn that whatever we have learned from our lecture number 1 to 4 in GOC series, we will apply them on that case, and all the questions like acidic strength, basic strength, stability of alkene, carbocation, carbon ion, the stability of them. So these will be covered in that MCQ practice session. Without a further ado, I am going to start today's lesson. Okay, let's begin. Our first effect is your inductive effect, the well-known inductive effect. The only thing you need to remember for inductive effect, number 1, it is a permanent effect. Number 2, it is a sigma bond phenomena. Number 3, it arises due to the electronegativity difference. So there are 3 things. Number 1, permanent effect, it is a sigma bond phenomena, okay, and number 3 is it is arises due to the electronegativity difference. Suppose I am taking the bond between carbon and fluorine. So what you can say, that fluorine is more electronegative than carbon, so this bond pair electron will be shifted towards the fluorine. It's the nature of electronegativity. As it has a higher electronegativity, so it will drag the bond pair of electron towards itself. So as a result of that, what you can see, that there will be some amount of delta negative charge over fluorine, and carbon will be some amount of delta positive. Okay. Now if I think that this carbon is attached to a long chain, carbon chain, then what you can see, that as this carbon becomes delta positive in the influence of that fluorine atom or more electronegative fluorine atom, now this delta positive, this is the first carbon, okay, this is the first carbon, second, third, fourth, fifth and so on. So what I can say, this first carbon is somehow delta positive. Now this positive charge will carry through the ring. So if we move from this direction, that is move away from the CF or the fluorine, what you can see, that there will be some amount of delta positive charge is arised or is induced over these carbon atoms. But the thing is that the amount of the delta positive charge is getting decreased. So the inductive effect keeps on diminishing from one carbon to another. So what you can say, that this inductive effect is nothing but your distance dependent effect. And the effect is something like that, after third carbon, it gets negligibly small. Okay, so you can neglect the effect beyond third carbon. So this is something you can think, that the charge is induced, one carbon is inducing positive charge to its adjacent one, and it is doing so. So this is why this is called the inductive effect. And whatever the system you are watching here, that means it is a fluorine atom, that means it nothing but pull electron density towards itself. It is pulling electron density towards itself. Okay, it is pulling electron density. So this will drag electron density. So what I can say, that it is nothing but your fluorine is nothing but your electron withdrawing group. It is withdrawing electron from the chain. You can think like that. So what I can say, that it is a electron withdrawing group, and this is called the minus I group, and the corresponding effect is called minus I effect. And there might be some group which is pushing electron density. Okay, so there might be some group like suppose I am taking this carbon chain and some Y group is there. Now Y is such that the opposite case is happening in this case. That means now it is pushing the bond pair electron, sigma bond pair electron to that carbon atom. So what will happen? This carbon will acquire some amount of negative charge, Y will acquire some amount of positive charge, and this negative charge will be induced and this effect will carry through the ring, and as you move from this direction the effect keeps on diminishing, and beyond third carbon it will be negligibly small. Clear? So this is the very basic thing what we need to learn in the inductive effect. Now these kind of groups are called your plus I group. So it is pushing electron density, that's why it is a plus I group. Now just take a look at these groups. Okay, so if you take a look at this order, you can see that over here they all are negatively charged. Okay, so as they are negatively charged, they are already electron rich, so there will not be any tendency to drag electron density towards itself, so they will rather push away electron density. So that is the thing what is happening here. They will exert the plus I effect, that means the electron donating effect. Clear? Now apart from these negative charges, you can see that there is a third degree carbon atom. Okay, this is a 3 degree one, and 3 degree alkyl group rather. It's a 3 degree alkyl group, it's a 2 degree alkyl group, and in this way 1 degree alkyl group. In this way it goes in this direction. So now my question is that why this kind of alkyl group is behaving as a plus I effect? That means why it is an electron donating group. Now if you take a look at this CH bond, okay, suppose you are discussing about CH bond. I know that there is a very slight amount of polarity or the electronegativity difference, but that difference, the electronegative difference, suggests that the carbon atom will acquire some amount of delta negative charge because it is to some extent more electronegative than hydrogen. So what you can see here, this carbon will be delta negative and hydrogen will be delta positive. So there will be a tiny dipole moment which is pointing towards a carbon atom. Suppose you are thinking about this CH3 group. So there will be a tiny dipole moment over that carbon atom which is pointing towards the carbon atom. So the negative end, so negative charge, to some extent delta negative charge will arise over this carbon center. Now suppose in a long chain there is a CH3 group. Okay, so it is somewhat delta negative due to the tiny dipole moment. The cumulative effect is occurring in this case. So what you can think that negative charge is induced over this ring and it will do over this ring. So in this way the plus I effect will be exerted to the system, to the chain or ring, whatever. So that's why the alkyl groups are behaving as a plus I group. Now more and more CH3 molecule suggests that more and more will be the strength, higher will be the strength of that plus I effect. Okay, so this is what happening in this case. Now look at this T is nothing but your tritium, D is deuterium, and hydrogen is your normal hydrogen, whatever. So you can think that this CT3 is more plus I, exert more plus I effect. That means that tritium exert more plus I effect than deuterium, and deuterium is more plus I group than hydrogen. Okay, so this is what this table says, that I am just erasing all of these. Okay, and I will suggest you to take a screenshot. Okay, now let's move on to our next slide, that is the minus I groups. Similar kind of thing is happening in this case also. What you can see over here, there is fluorine atom. Okay, fluorine is more electronegative and there's a positive charge, so it's a highly minus I group. That means it will try to drag electron density, sigma electron density of course, towards itself. The same thing is happening in this case. Look at this, nitrogen, oxygen, sulfur and oxygen, nitrogen is present, oxygen over here, this carbon is sp2 carbon. Remember this C double bond O, the carbon is sp2 carbon and sp2 carbon is more electronegative. So what will happen in all of these cases, the minus I effect is operating. Look at this molecule, okay, this molecule or this group, that is this alkyne group. There is a alkyne group. Alkyne group is sp carbon atom which is more electronegative than this alkene, because this alkene has sp2 carbon atom. Okay, so this is what happening in this case. And now look at this fluorine is more electronegative than chlorine, it is even more electronegative than bromine, and iodine is in the is even less electronegative than bromine. So this is the series what we can think about the strength of the minus I group. Okay, so I am erasing all the inks, and so that you can take a screenshot of this. Okay, let's move on to our next effect. I think that up to this it's okay for your inductive effect. This is the basic of your inductive effect, and more thing we will learn in the problem solving session. Okay, now moving on to our electromeric effect. Electromeric effect. One very interesting feature of this electromeric effect is that it's a temporary one. It's a temporary one, and it arises when reagent is there. In absence of reagent, there is no this kind of effect is observed. And the third point is that pi electron is involved in this case. So temporary, reagent specific, and pi electron is involved. Only these three things you need to remember. Now what is actually happening? You already encountered these terms, these reactions. Whenever a alkene molecule is reacted with the some electrophile, so it donates electron density towards itself, and it forms something like this. Okay, this kind of E plus, you can think that it is your bromine molecule. Okay, it acquires a cyclic bromonium ion. This kind of thing is happening. So in this reaction, what you can think that and not always a cyclic structure will obtain. There might be this kind of observation you can think, whatever. So whatever the case is, the electron density is donated towards that reagent, that means the electrophile itself. So this kind of effect is called your plus E effect. Here electron donation is taking place. From substrate the electron is donated, pi electron is donated to the reagent. If you remove the reagent, there will be no donation, there will be no such kind of effect. So it is not the effect of the such discrete molecule. Whenever some reagent is there, so that pi electron of that molecule will behave accordingly. Likewise, you can think that suppose there is a C double bond over here, and now you are adding some nucleophile. In presence of nucleophile, what will happen? This nucleophile will attack at this position. Okay, so there will be something like this. Okay, something like this will happen. So here what is happening? Electron density is approaching towards the C double bond. That means a double bond. So this kind of pi bond is accepting electron density from nucleophile. So this can be termed as your minus I effect. So this is sufficient for your electromeric effect. Now moving on to the next one, that is your resonance. That is your resonance. Now question arises that why we will study resonance, and from which observation we actually start thinking that this kind of effect exists. The observation is that in a benzene molecule, okay, suppose you are taking a benzene molecule. Over here what you can think that this is a C double bond C, and you know that C double bond C has a bond length around 1.34 angstrom if I am not wrong, and this C single bond C, okay, the bond distance of C single bond C is around 1.54 angstrom. So this could be reflected in this case, but in observation what we can see in reality, we see that all of these bond lengths are your 1.38 angstrom. Okay, all of the bond length is 1.3 angstrom, and this is how we write benzene ring. So what is the significance of this circle and why this kind of thing is happening? The answer is resonance. Resonance is nothing but your delocalization of your pi electron. Delocalization of your pi electron. Okay, and what is the condition for the resonance? Condition is your planarity and parallel orbitals. Only these two conditions are sufficient to describe the resonance. What you can think that in benzene ring all carbon are your sp2 carbon. Over all carbon atoms are sp2 carbon atom. So what you can see that sp2 has a bond angle of 120 degree and a geometry is planar triagonal. So these all carbon are present in a plane, and perpendicular to that plane there will be some p orbital. Okay, now you can think that over here there is a pi bond, sideway overlap between these p orbitals. This is the case what you can write in this case, the benzene ring. Now what is another alternative? Since these all p orbitals are parallel to each other and the whole molecule is in a plane, so there will be a possibility that this bond will shift here, this bond will shift here. So now the overlap will occur in this way. Now these two p orbital is overlapping. Okay, these two p orbitals are overlapping, and here this is the happening. So what you can think that that why this is happening? Now pi electron is to some extent delocalized over the ring, and whenever there will be electronic delocalization, the molecule gets stabilized. So resonance is nothing but a stabilizing effect most of the cases, not for always, but most of the cases we see that resonance gives stability to the molecule. If there is no resonance is present in a molecule and some molecule you are taking that there is resonance is present, then you can easily say that that resonance is nothing but stabilizing that molecule. Okay. Now the point is that the resonance is a permanent effect. It's a permanent effect. It's a permanent one, and it's a strong effect. It's a strong as well. Okay. Now the resonance is not diminished or is not decreased over the chain. So if as long as a conjugation will present, resonance will remain intact. There will be no change in the strength of the resonance, or the effect will not alter. So conjugation is another fancy name of resonance. Suppose it's double bond separated by single bond, it is another double bond is separated by single bond. In this way, this kind of assembly is there. You can think that. So what you can think that this bond will shift here, this will shift here, this will shift here, and it will be something like this. Okay, so over here double bond, double bond, double bond, it is a negative charge and a positive charge. So this you can think is happening. So what you can see that as long as the conjugation is present, there will be resonating effect is showing, and there is no question of the diminishing effect or decreasing effect. Clear? So resonance is a permanent and strong effect. It is a very strong effect. Now point is that what are these structures? Okay, what are these structures? These structures are called your resonating structure, okay, or your canonical structure. Now obviously these canonical structure or resonating structures are nothing but your imaginary one. They do not exist in this way. What you can think that over here it is one resonating structure, and this is another resonating structure of benzene. It is shifting here. Okay. Now I am adding this third bracket. So inside the third bracket I am showing the resonating structures. Okay. Now what I can say, what we observe in reality, that over this benzene ring the double bond character is shifted. Okay, so the pi bond is delocalized over the ring, so there will be a partial double bond character over all carbon atom. So all the CC bond has some partial double bond character. It's not a fully double bond, it's not a fully single bond, because of that pi cloud delocalization. Clear? So pi electron is circulating over here, so this circle implies a pi cloud circulation. Clear? So what I can say that this is the structure of the benzene, which implies there is a pi cloud delocalization, and this is nothing but one hybrid. This is called your resonance hybrid. Okay, this is nothing but your resonance hybrid. Okay. Now we will discuss about two groups. One is your NH2 group, okay, and another one is your CHO group. One is your NH2 group, another is your CHO group. For NH2 group, there is a lone pair over here. What you can see, that lone pair will be donated here, and this will form negative over that ortho position. So this is what is happening. Clear? And now this negative charge will keep on moving throughout the ring. So there will be some other resonating structure you can get. So this is a case where the electron density is donated to the ring. So this NH2 group, you can think that this NH2 group, okay, this NH2 group is nothing but your plus R group. Plus R means it is pushing electron density to the ring, okay, And now over here what you can think, that there is no such lone pair available. So this double bond from the benzene ring can be donated to the CHO and it will produce a O negative over here, and this something like this you can see. Okay, there will be positive charge, and now positive charge is circulating throughout the ring. So these all are nothing but your resonating structures, whatever. So what you can say, that here the benzene ring is donating electron density, so CHO is accepting electron density, it is pulling electron density. So this CHO is electron withdrawing group and it is called a minus R group. Clear? So this is what is happening, and I will give you some examples of plus R and minus R groups in the next slide. But before that, how many types of conjugation is present? Let me discuss. So broadly there are two types of conjugation. One is in this type of conjugation, which is called a linear one. Okay, this kind of conjugation is called linear conjugation, negative positive. This is called a linear conjugation. And there is another type of conjugation is present, which is called your cross conjugation. Cross conjugation means, now if you take a look at this, it can come here to produce this kind of resonating structure. This will be negative and positive over here, and there's a possibility that it can go here also. So by going there, it can form this kind of system where there will be negative charge over here and positive charge over here. So this kind of system can occur. So this double bond, okay, so what you can see, that this double bond can go either this side or this side. In both way it is getting the conjugation. So this is the conjugation happening. This is why the conjugation happening, and this type of conjugation is called your cross conjugation. Now another point is that in which cases you will see conjugation. In which cases you will see conjugation. So now double bond, single bond, and if here a double bond is present, there will be a possibility of conjugation like this way, as you can see. Now there is another case, that means this double bond, single bond, and over here there is a negative charge. That negative charge can come here to produce this kind of resonating structure over here. So here also the resonance can occur or conjugation can occur. There may be the conjugation if this double bond, single bond, and here a positive charge is there, that means a carbocation is there. There will be this kind of conjugation. Okay, so here also conjugation can present. Now if double bond, single bond, and one heteroatom containing lone pair is present here, so what you can say, that this lone pair can be donated over here and that can form this kind of assembly. There will be something like this. So these all are the possible cases where the resonance is occurring, and in all cases the condition is maintained. The orbitals are parallel orbitals, and there's a planarity in the molecule. So this is how the reaction, the resonance or conjugation is happening. Okay, now let's move on to our some plus R and minus R groups. So over here you can see that these all are your plus R groups. They are all are negatively charged, so they have a common tendency to donate the electron density through the conjugation. Okay, so this negative charge can take part in the conjugation. This lone pair can take part in the conjugation. Okay, now look at this. Oh, this lone pair is donated over here in this way. So this lone pair can also be donated over here. So in this way they are taking part in conjugation. This phenyl ring is donating electron. You know that when CHO is attached with respect to the phenyl ring, what you can say, that phenyl ring is donating electron density. Clear? Now over here you will see this kind of halides. This halide has lone pairs and that can also donate electron density, but there's a case that whenever this kind of halide, okay, this could be fluorine, chlorine, bromine, iodine, whatever it is. Now I am writing it over here, that whenever halide is present in benzene ring or phenyl ring, whatever, phenyl ring, so what you can say, that only consider inductive effect, because they are very weakly plus R group. Their plus R effect is very weak. So and there will be some amount of orbital mismatch, because in benzene ring or in case of the phenyl ring, what we can see, there is carbon is 2p. So although the fluorine and fluorine has 2p, and there will be some amount of overlap, but the chlorine, bromine and iodine, in those cases the p orbital is of more the p orbital has a greater size. So as a result of that, what you can say, that there will be orbital mismatch, so that will not be a good candidate for your plus R group. And for fluorine, one interesting feature is that fluorine is very much electronegative. So it generally don't want to push the electron density towards the benzene ring, rather it will drag electron density through the sigma bond. That means the minus I effect is pronounced here. So always consider the inductive effect whenever this kind of halide is present in a benzene ring. We will apply this kind of system, or we will apply this concept in our MCQ solving class. Now moving on to our minus R groups. Now look at this. Here a positive charge over here, that means it has a tendency to drag electron density. Suppose what I can say, that suppose there's a double bond and CH2 plus is there, so I have already discussed this term, so it is dragging electron density towards itself. So this kind of minus R effect can be exerted by CH2 plus. For NO2 has structure something like this. So if double bond is present over here, so it can accept electron density, so it is nothing but pulling electron density towards itself. For cyanide, same case is happening. Suppose over here double bond is present, it will come here. So similar kind of observation, you can think that for this kind of C double bond, remember whenever this kind of C double bond is present, these all exert your minus R effect. Why? Because suppose a double bond is present over here, a double bond, and this C double bond O, and whatever the group it is, so it will come here, it will form this kind of O minus. It could be your aldehyde, it could be your ester, it could be your anhydride, this ester, anhydride, acid, carboxylic acid, amide, whatever it is. This kind of thing is happening. So these all are your minus R group. Okay, so one thing I have forgot. Okay. Erasing all the inks. Now you can take the screenshot of this minus R group. Okay, and this is my previous slide. I am erasing all the ink. Now you can take the screenshot of this one. You need not mug up all these things. What you need, just focus on the structure, and then you can easily identify that which will behave as a good plus R group, good minus R group. So these are very important for your understanding purpose. Now question arises that what is the stability of the canonical structures? Over here I am saying that there are two canonical structures is there, structure number 1 and structure number 2. In both the cases, what you need to say, that these all, in both the cases they are imaginary. You know that these canonical structures are imaginary. But why we will study this thing? Because the more the stability of that canonical structure, there will be the greater contribution of that canonical structure to the hybrid structure. That means whatever the structure I am getting, that hybrid structure, resonance hybrid, so that will resemble with that canonical structure which has a more stability. So we need to understand that what will be the pattern of this canonical structure and what will be the stability of them. So number 1 point is that, now remember that you must follow them in this order 1, 2, 3, 4 sequentially. Whenever you will compare two or more canonical structures, first consider that where the number of bond is higher. If higher number of bond is present, then automatically the octet fulfillment, this criteria will be fulfilled. Second point is that where the lesser number of charge is there. Suppose one is neutral molecule and somewhere you are getting some charge separation, so go for the neutral molecule only when the number of bond is same in both the cases. Number 3 is just like charges apart, because you know that positive or negative repel each other, and positive negative attracts each other. So that's why like charges far apart, unlike charges closer to each other. That will be a condition for the stability. And the third point is that the electronegative atom will have negative charge. So these 4 points you must consider whenever you will discuss this kind of stability of the canonical structures. Now moving on to these two system. Okay, moving on to these two system. In the case of 1, how many bonds are present? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So there are 13 sigma bonds. There's no pi bond over here. And here we can say in 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There are 13 sigma bonds. There are 13 sigma bonds, and there will be over here one pi bond. So greater, there will be one pi bond. So greater number bond is present in the canonical structure 2, and you can also think that it's a carbocation. It's electron deficient, octet is not fulfilled. Whenever this kind of resonating structure is occurring, that means this kind of double bond is present, pi bond is forming, then there will be octet fulfillment of the carbon. So the first point suggests that the second one is more stable than the first one. So second canonical structure will be more stable. So in the resonance hybrid, the contribution of the second one will be greater. So this is the case. Now if you follow the fourth rule, then you can say that oxygen is more electronegative, so it will not allow the positive charge. So for the fourth point, if you consider only the fourth point, you can say that the one will be more stable. But that's not the case. You have to go sequentially. Number 1, number 2, number 3, number 4. You have to follow this sequence. Unless you can't get the right answer. Now let's talk about the hyperconjugation. In some molecule, what you can see that there is no conjugation, but they will try to behave as a conjugated system by temporarily breaking some weaker bond. The thing is that suppose you are taking this molecule. Over here, what you can see that in this molecule there are this kind of C double bond C is present. C double bond C, this is sp2 carbon, this is sp2 carbon, but it is sp3 carbon. Now sp3 carbon is not in plane with that system, so there is no conjugation is present. Now what I can say, suppose I am breaking this CH bond. Now carbon is more electronegative than hydrogen. Now if I break this CH bond in this way, okay, so what I can say, there will be a negative charge over here and H plus, and this negative charge will come here to take part in the conjugation. But remember that this is doing to gain the stability, extra stability, but it's not like that it will it will remove the hydrogen H plus. So what will happen, the bond breaking is occurring for a very shorter time period. So you can think that for a very lesser amount of time, for a fraction of a second, so it will break the bond, it will become C negative, that will form a conjugation like this one. Okay, so that will form a conjugation like this one, and now again it will come back to get the CH bond again. So what is happening, there will be this kind of fluctuation over here, and it will gain to some extent stability. It will not like that it will completely release the hydrogen, because then it will be a charged one, which is not the stable. So it is present as it is, but what you can see that this CH bond, it has bond order slightly lesser than 1. If it is 1, that means a complete CH bond is present. So what you can think, it's not completely broken, but the bond order is not exactly 1. It's slightly lesser than 1. When it is slightly lesser than 1, it suggests that some amount of bond breaking is taking place. Some amount of bond breaking is taking place, and that is actually leading to the hyperconjugation, and hyperconjugation leads to the stability. This is what you can get here. Now what you can say that with respect to this double bond, okay, with respect to the double bond, it is your alpha carbon atom. So what we can say that more the number of alpha hydrogen, these all are your alpha hydrogen, more will be the stability. This is the case of hyperconjugation, because more and more alpha hydrogen will lead to this kind of hyperconjugation structure, and hyperconjugation structure will give some amount of stability to the system. It's not like that it will give stability as much as resonance can, but it will stabilize the system. Even if you follow the order of stability, which we will apply in my next class, R greater than H greater than I. So this is the order. That means the most pronounced effect is your resonance effect, then your hyperconjugating effect, then your inductive effect. So this is the priority. So hyperconjugation makes a molecule more stable than inductive effect can. Although it is lesser stable than resonance, but one kind of conjugation is present here. Look at it. That's why it is there is another fancy name of hyperconjugation is no bond resonance. No bond resonance, and it is also known as Baker-Nathan effect. Whatever the thing is that here weak bond is broken. Whatever the weaker bond present in the molecule will be broken, and in this way there will be a suitable arrangement of the conjugation where you can acquire this kind of conjugation. Okay. Now there will be two type of this kind of bond breaking. One is that this kind of CH is present, CH3. Okay. So what you can see that CH bond is broken to produce this kind of CH C negative and H plus, and it will take part in the hyperconjugation. This is one case. Another case is that very high electronegative atom is present like CF3. Now the bond breaking will be in the opposite direction. That means fluorine is more electronegative. So what you can think that it will form a F minus. So there will be CF, CF, some amount of positive and negative, and now there will be this kind of hyperconjugating structure. So what you can say in the first case, this CH3 effectively pushing electron density, so it is called a plus H effect. And in the second case, this CF3 is dragging electron density from that double bond, so it is your minus H effect. First one is plus H effect, second one is minus H effect. Clear? And the last point what I need to say, for CH3, CD3 and CT3, that means hydrogen, deuterium and tritium, the bond strength of CH is weaker if you follow the bond strength order. Okay, so the bond strength of CH is lesser than CD, it's even lesser than CT. So from this concept what you can say that the plus H effect, these all are plus H group. Okay, so the plus H effect of CH3 is greater than CD3, is even greater than CT3, because weaker the bond, more will be the hyperconjugation. So this is the rapid revision of your electronic effects. I hope you enjoyed the lecture and understood all the topic. These are very elementary basic things, but these are very essential also, because we will apply these things to our next classes, that will be purely your MCQ solving classes. So keep following, and if you enjoyed it, then please like, share and subscribe. Thank you. Happy learning.